Okay, so if I want to give you the overview of the spice code, so let us jump into the electric tool. So I have already built the circuit, that is the schematic, as you can see over here, and I'm not going to give you the explanation with respect to how I have built. I have built the same thing what I have shown you in the previous couple of examples, like here, the same circuit I have built over here. And one important thing I can just tell you here is whenever you're going to put the PMOS, when you put the PMOS over here and when you change the width to 20 and length to 2, try to make this upside down, because here by default when you bring and place this PMOS on the screen, the below portion is your source, but when you're connecting it to the VDD, the source should be connected to VDD. So hence I should be making this particular thing mirroring up down, right? So I have done it for all the gates, I mean all the MOSFETs, and I have tried to connect it according to the schematic, and I have written the spice code. Now the main agenda here is to make you aware of what exactly is the spice code. Now as you already know that I'm going to represent my VDD, ground, and all the inputs with the starting alphabet V, because that is the fundamental rule of any spice code. So I have taken V1, V2, V3, V4, V5 to represent any signals. So first two terms represent the VDD and the ground, and the third term represents the a signal S, that is select line. And here I have taken the pulse. So I have taken S is the name of the signal, and it is indication that the signal what I am taking is a square pulse, or basically a pulse of different duration. Now there are different terms that are coming over here, so let me give you a brief about what exactly these particular values mean. So 0, the first 0 indicates the pulse is starting from the 0th uh, 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 initial value will be a 0, that is starting from the 0th level, that is 0th time, and then pulse indicates it's a square or a rectangular waveform. And 0 5, this indicates 0 is the low level logic, 5 is the high level logic, and these three zeros indicates, out of this the first 0 over here, this indicates the delay. That means whenever you start the signal, whether you want to start the signal at the 0th time instant or you want to delay the time signal for some duration of time, so that is indicated by this. I'll also show you about that. And these two indicates the rise time and the fall time of the pulse. So typically I can keep it as 0. So the moment I keep it as 0, you'll see there will be some rise and fall time that will be automatically considered, or else if I whatever value you want to put, you want to give, that you can give in terms of some picosecond values. So these are my rise time and fall time, and these two last line indicates 8 nanosecond is the total on time of the pulse and 16 nanosecond is the off time of the pulse. Like for example, if I just want to show you what exactly the terms mean, if I have a pulse like this, so the initial value is 0, means my pulse starts like this. So this is my 0, so that is indicated by this particular line. 0 5 indicates the 0th voltage, that is low voltage, and the 5 is the high level logic. And this indicates delay, so no delay has been incorporated, so nothing, which means the signal is starting from the 0th time instant. And this 8 nanosecond and 16 nanosecond, so that means I was telling 8 nanosecond is my on duration, which is this, and 16 nanosecond is the total pulse duration. That in turn makes my off duration also to be equal to 8 nanosecond. So I can play around with these to set the different pulse values. Similarly, I have taken the values for my signal A and signal B with the different pulse duration. So if I take all the pulse duration of the same duration, then I will not be able to get the different logics. See, because when I try to give you the values of the truth table, and truth table, like how should I get? I should get the different values, right? So for that scenario, I'll be taking the pulses of different time duration. And then this is my capacitance, load capacitance I have taken between the output terminal and the ground. So 0 indicates the ground level, and I have attached assumed value 50 femtofarad, and by changing this 50 femtofarad to different values, I can change the rise time and fall time of this entire output. So this plays a very crucial role. I'll talk about that sometime later. So you can just consider a minimum value of 50 femtofarad. And then there is a dot measure. This is a dot over here. Dot measure. You have to do the measurement. What measuring you are supposed to do? We are doing the transient analysis. TF indicates the fall time, and I'm triggering the output. I'm measuring the fall time at the output ping, and since I'm measuring the fall time, the initial value will be from the 4.5, and fall equal to 1 indicates, this indicates it's not that from 4.5 to 1, it is not that. Fall indicates that fall is logic 1, means you are measuring the fall time, and this TD is equal to 20 nanosecond indicates you are supposed to wait for initial 20 nanosecond of time before you start measuring the fall time. You can keep any values over here. That only indicates that you delay the measurement whenever we try to measure the fall time or the rise time for the first instant of time. So whenever we try to measure the rise time and fall time, it is indicating that you wait for initial 20 nanosecond of time. Just that's because to ensure setup and hold times are being properly managed by the signal. And my target is my output V of out, and value will be from 4.5 till 0.5 volts. I am supposed to do the fault time analysis, and again I'll be quoting fall equal to 1. That means you're doing the fault time measurement. The same is the case here. I'm doing with respect to rise time, and here my value will be 0.5 till 4.5. Rise equal to 1. That means you are doing the rise time analysis, and you wait for 29 seconds of time initially, and you mention what is the duration of transient analysis you want to do. Dot try from 0 to 100 nanosecond, and try to include the C5 model files that is present in your directory. So I have done that. So let me try to run this. So simulation, right, spice tech. If it is asking to save it, save it. Now here, once you run it, if at all this particular spice code is coming out with dot option error, you can just remove all these things which are shown in the color font, and my main spice code is the one which you can see over here. Fine. So let me save it and let me run it. So I got the output. Let me make it large, and I'll do the add plot plane. So I require 4 plots. So one is my input signal A, another is my input signal B, and the third one is my select line S, and the fourth one is my output. So this is my multiplexed output, 2:1 multiplexer output. Now let us try to understand the output with respect to input. See, the as defined, as we have discussed in the truth table, whenever S is having a value of 0, let's say we'll consider a value here. Yeah, whenever S is having a value of 0, my output will be connected to A. So A has a value of 0, so that 0 will be coming here, the output. Whenever S goes to 1, whatever value that is present in B, that will be coming. So in the B, I have this particular signal, and the same signal will be replicated at the B. And you can cross verify at any point of time. As you can see, whenever S is having a value of, let's say here, a value of 0. So value of 0 means A. So look over here, whatever the content that is present here, that will be C. Just a moment. We'll try to put it like this. Yeah. See, whenever I have S equal to 0, whatever value that is present in A, that will be coming at the output. So this completes the analysis of the multiplexer. Now let us try to understand where do I get the rise time and fall time of this entire circuit, because that's where I'm going to get the analysis. So go to the view. In the spice error log, you can see what is the fall time. So this is my fall time, 2.1 into 10 raised to minus 8 seconds, or 0.2 into 10 raised to minus 9, that means 0.2 nanosecond. And fault rise time is also 2.38 into 10 raised to minus 8, and this it has been measuring from this point of time till this point of time. So this is the rise time and fall time, and this rise time and fall time will change if you change the value of the capacitance. Like for example, in this entire same setup only, I can minimize this, and I can do the spice code alteration here only. Rather than doing it in this particular setup, I can do the spice code variations here in the same LT spice window. See, the moment I change it to 100 femtofarad and you save it and you run it and then go to view and spice log, as you can see it has changed. So based on the value of the capacitance, the rise time and fall time will change because that indicates the amount of time it is taking to charge that load capacitance. But anyhow, we are going to fix up that 50 femtofarad of the load capacitance constant, and we are going to do the analysis similarly for all other circuits. So this is how your spice code analysis is being done. And on a similar line, whatever is the amount of input, you can give different values. Now here I was telling, if I want to give the delay, see, as you can see, all my signals are starting at the 0th instant of time. Now if I try to give the delay here, let's say for S signal, I give it as 10 n, that means start the signal S after 10 nanosecond, which means my S signal, this red color signal, will start after 10 nanoseconds. See, once I do this changes, save it and run it. See, as you can see, the delay has been given as 10 nanosecond. So that is my delay. And if I want to incorporate the rise time and fall time for my signals also, I can do that over here. So I can give it here 2 pico and then 2 pico, and I'll save it. I can give, see, the rise time and fall time has been given to pulse S, and this is giving you exactly a square pulse. In fact, when I use 0, it will take automatically some random value of rise time, but when I use some value in terms of picosecond, it is going to give me exact square pulse. So I can incorporate my rise time and fall time like 2 pico for all my signals. So to give you a idealistic view of this pulse in terms of its square, see, I can see. So everywhere I given 2 picosecond of rise time and fall time, I save it and I run it. All the pulses are in a square manner. See, and accordingly your output will be same. So this is the analysis of your 2:1 multiplexer based on the truth table that we have designed. Now there are multiple ways of getting the logic. So other logic, let me just show you, which is my static logic, I think, which you are going to, or which you have implemented already. The same static logic you try to implement and the spice code won't change. As per the number of inputs and select line, the spice code is going to remain same. So give the input accordingly and you will be getting the output. So this is how your entire analysis on the 2:1 multiplexer will work out.